Hello. Today we're talking about SCNN. So that's sparse CNN, an accelerator for compressed sparse convolutional neural networks, as a part of the presentation assignment 2 for E699. So this is a paper published in 2017. So these are the general outlines that today's presentation is going to talk about. The introduction. So sparse CNN is a CNN architecture for exploiting the sparsity in weights and the activation. So basically, what it basically does is that it kind of compresses the weights and activations so that they can be uh, transferred easily from the DRAM to chip, as well as during the chip transmission, as well as for other operations during multiplications as well. So it achieves a speed of 2.7 times and the energy reduction of 2.3 times. So for the activations, what it's trying to explore is that, for example, using some non-linear functions such as ReLU, the ReLU function clamps all of the negative values to zero. So then we don't need to multiply by zero anymore, because multiplication of zero is automatically zero, and obviously adding zero is the same number as well. So it kind of removes that kind of redundancy. And for the weights as well, for the weights, zero weights, the multiplication is the same, so it kind of removes that as well. So it uses multiple processing elements which only multiply the non-zero weights and activations, and they use something called Cartesian product. And then it's use some data flow known as PTIS CP sparse data flow, which we'll talk about later on. So the main goal of the paper is obviously to develop an accelerator for CNN, which utilizes the sparsity in both activation and weights. It introduces a novel data flow for that, and then it reduces the memory bandwidth and transmission cost using the compressing coding techniques. The Cartesian product does two things. The first is obviously it kind of doesn't have the zero operands for multiplication, so it kind of avoids that. The other part is it does a parallel multiplication and then coordinates the partial sums later on. And then the multiple P architectures are used so that they can be used alongside tiling to avoid something called an output halo. And then it kind of compares the performance and energy of SCNN with the dense neural networks, as well as it measures the sensitivity of the sparsity on the performance and the energy efficiency. So basically, a lot of papers have done about the weight sparsity, and then proving the weights, and then retraining that. The case of activation sparsity is quite different, because it depends on the dynamic state that is during the runtime. Depends on the inputs and stuff like that. So basically, one of the examples is the relay activation, which I have mentioned before. So for the paper, it uses three models. Or three CNN architectures: LXNet, GoogleNet, and VCNet. So these are the basically the conventional number of layers and the activations, the weights, and the number of multiplications that requires. So as you see in the right hand side, we have the three diagrams. So that's the same for LXNet, GoogleNet, and the VCNet. So let's look at the direction for now. So the y-axis gives the density in terms of input activation and the weights. The blue one is input activation. The red one is the weights. Let's forget the triangle for now. So what it basically says is that for the one, that basically means that all of those values are dense. That means there are non-zero values only. And as it grows lower, basically means that the gap between one and the number is zero value, which we can kind of avoid or kind of remove. That's the sparsity in the data itself. So as the model increases, both IA and the W, right, the weights and the input activation, becomes more sparse. So that basically means that we have more zero values, which we do not need for multiplication and addition. The same follows for the GoogleNet inception modules, right? And as well as for the VCNet as well. Uh, and the same data is also represented by the left, so the right hand side of the y-axis, the number of multiplications, number of multipliers. So what that basically says is that As there are zero values, so multiplying by zero doesn't make any sense, right? So the number of multiplication is reduced, let's say here by 70, it's just reduced to 70%, and at the bare minimum, it can be reduced to around 10%, right? So only 10% of multiplication is yielding the correct or yielding the useful result. That's basically what it's trying to say. And the other part, there are other sparse accelerator as well. So some are listed here. So the iris only uses the activation uh, sparsity, and then it uses row stationary data, right? And then the convolutine uses the activation sparsity using ReLU, but doesn't use weights for that. The Cambricon uses weights, but it still doesn't use activation, so that when the activations are zero, it still does the computation, which is not efficient. But the SCNN, the paper that we're talking about, uses both activation and weights. And the other part is that it uses the compressed data, not for only the transmission of data, but also the processing. So all of the on-chip data will also be in compressed form as well in the DRAM. So that's kind of a good thing. And it also uses something called Cartesian product, which would optimize the multiplication part that we'll talk about later on. So it's a unique thing as that it uses both activations and weights. So just for the terminology that we're going to use, so we're going to say that the weights are in the dimension of R width and S height, or we can say R by S, right? Then we have C channels for that, and we have K such weights. The inputs, we have W by H inputs and the C such channels, and we have N inputs for that. And relating to that, we have N outputs. The W and H will be W minus R plus 1. So this basically is the convolution output formula, right? We just assume that the padding is 0 and the stride is 1. And we have for the k different filters, we have k different outputs for each of the input, right? So this can also be displayed in this kind of a loop. We have a 7-dimensional loop here for all of those values, and then obviously the loops can be moved up and down based on what kind of data flow we are trying to achieve. And then this the same is also represented in somewhere like this, right? So this is the same thing. It basically means that the N loop is has K loop, and it has C loop and W loop and so on and so forth. So we just use this representation later on. So the paper uses data flows are called as PTISCP sparse. So that's the inertile input stationary Cartesian product sparse data flow. So we just talk about that in brief. So the first part is input stationary. So what that basically means is that the input will be stationary, or input will be stay static in a PE, and we will be changing the weights, and then obviously we'll taking out the partial sums out of that. So for that, what we basically do is that this number of filters, so we shift that inside here, right? So that's what we did right here. So what we basically do is that for a given channel, the input W by H will be same, and we'll be running that for a different K by R by S, or for different K filters, right? But then again, we can't store all of those K filters inside our on-chip memory. So what we basically do is we just divide these K filters into K by KC groups, or divide by into K in the size of KC, right? For example, we have 8 filters, then we can divide them into let's say a size of 2. That's what that basically means we have 4 groups, right? So we just divide it into group so that we can store that inside our memory. So because of this, now we have to use KC here, and this will be our final loop, and we have to do this for 4 times, or k by kc times. So we just have to add another loop in the front. So after each group ends, we just we just take out the weights and just replace it by the new weight of the new group, and then also we have to take out the partial sum from the buffer, and then we just have to output that somewhere else, right? So those two things are added, but it helps to store those in memory, so that basically optimizes in the long run. The other part is Cartesian product. So what it basically means is that we have a array of multipliers. So it basically shows the intra-PE parallelism. So we have, let's say we have 2 inputs. Let's not forget about matrix right now. For now, we just assume vector. So we have 2 and 3 as input, and 4 and 5 as output. So we have 2 input and 2 weights. So we need to have 2 by 2. So this is number of weights F, and this is number of inputs I, right? So F into I array of matrix. So that's like 4 for now. So we have multipliers for now, and for each of the multiplier, we'll do each of the different multiplication, right? So here we send this 2 here, and this to send the 2 here as well, and then we send the 4 here and send the 5 here, and then do the multiplication. So we have parallel multiplication or simultaneous multiplication, so that we can have multiple results, right? So why we basically do that is because all of those multiplication would be required sometime later on by some other filters or by some other cases, right? So we'll be storing them into the specific partial sum part into the output buffer, right? So we'll just have some coordinate system so that each of those multiplication will be stored into the accurate coordinates. The other part is planar tile. So planar tile is basically tiling of the inputs, right? So since all of those inputs will not be processed by the same P, so we'll just be distributing the part of the input to multiple P's so that they can operate on the weights. So we just tile the C by W by H into C by W, T by W, S T, uh, and then distribute them across different processing elements, and the weight will be broadcasted to each of them, right? So let's say we have a 2 by 2 weight, and then we just tile them by a 2 by 2 as well. The issue here is that, for example, if I have a weight of 2 by 2, right, then we have to multiply all of those with these values, right? But then we have to slide one window, and we have to multiply it by this part as well. But then again, we have the first two rows and columns stored in a single P, but the second the next two rows and columns will be stored in the next P because of tiling, right? So that poses an issue. So to avoid this, we have two options. The first one is input hello, and the second one is output hello. So what the input hello does is that the P doesn't just store the first 2 by 2, but also store a additional part there, right? So we don't need this part. We can just avoid this part. So this part we can add this part as well. So what it basically does is that we have some additional data in the P so that it can compute the partial sum, right? But then again, the paper actually uses something called output hero. So we actually store the 2 by 2 sum, right? But what we do different is that when the filter moves through this, let's say the filter moves through this, right? So first it will move here and will calculate the partial sum, right? And then it will move here. But then again, you only have this data and not this data, right? So what it basically does is it just computes the partial sum for this data, which is incomplete. Obviously, we have to do the partial sum of the other part as well. And then it kind of sends it to its neighboring P, right? Which would have this part of the sum. And then that they will just add that up. So that's something that the paper is trying to do, something called Panner. And then this is the pseudocode for obviously the dense part. Now this is not for the sparse part. So we have this A and the B, right? So what the AV loop does is that it's kind of this is for the grouping, and this is for the tiling, and this is B, and this is obviously D, right? So this is for buffering or taking the data from the buffer, the inputs and the weights. And this is the part of the Cartesian product. So we have the parallel product of the both of the F by I multipliers, and we have to calculate the coordinates as well, because though each of those products needs to be added to the specific points in the output matrix, right? So for that, we kind of calculate the coordinates, and we then add that up into the exact coordinate that we need to, and then at the end we'll just add them all again, right? So that's for the dense one. So for the sparse, we have to do some modifications here. So what you basically do is that uh, so instead of storing all of those, like getting all of those inputs, we'll be taking some compressed blocks. So the weights will be stored in a compressed sparse blocks of Kc by R by S because of the Kc grouping, right? And the inputs will be Wt by St to tiling, and then we'll store that into compressed sparse blocks because we'll be only taking the non-zero values for that. And then we also be using some encoding for that. We'll just talk about the encoding later on. And then we'll be distributing that data instead of entire data, right? And then obviously the multiplication will only have the non-zero values, and they won't be taking any zero values. And then for this, then the case it becomes is that we won't be having complete F by I data, right? So we'll have smaller than that. But then we have to move that into the entire output space or the output matrix. So how do we do that is that we use something called a scatter crossbar network, which scatters this multiplication into their specific places in the buffer. So just to make sure that the buffer has enough space for that. So the buffer would have something higher than the FII space. So we have 2 times f by I buffers to store all of those multiplications and all of those stray one as well. And then the buffer can again be drained and compressed again. So this is a general architecture of the SCNN. So we have multiple P's, and then we have a DRAM here, and each P would have some IA and OA, so that's like input and output activation, and the words coming in and out, and then you can communicate along with each other just to for those halos part, right? So we can just do that communication as well, and the data will obviously be distributed to all of those parts. The weight will be distributed, the input will be tiled, right? So inside a P, we have actually something like this, right? So what this architecture is that this is the weight, this is the input activations, and this is the output activations, right? But since they are sparse, so we have some kind of encoding with that. So we have the data as well as the index. So the index will be stored here. So that we'll just talk about the index later on. And then what you do is that this is the FII multiplier. So the weights and the obviously inputs will go here and they will just multiply all of that, right? As well as they will also take the indices value for the coordinate computation just to make sure that each of those multiplication need to be stored in a specific place, right? And then this coordinate will define whether the product should be stored to. And for the storing of the product, we have something called a crossbar scatter here. So what basically does is that it helps to scatter all of these FII products into different buffers, right? So these are the accumulation buffers, which have a uh, sorry, which has an adder in front of it. So we just adds it to the specific buffer, and then it just flushes them out to a post processing unit, which kind of handles the halos. It kind of it shares the incomplete sums to other neighbors, and then just to the relay activation, as well as the pooling and other parts in this specific layer, right? So this is how all of those things would work, and then obviously the output will be stored to the output sparse and the output indexes. And this also kind of does something, right, moving the output sparse to input sparse, because the output of one layer would be the input to another layer, right? So when you are just doing the part for the another layer, we can just move the output from here to here, right? So that's something this paper does as well. So that's basically what this part is trying to explain. Obviously, the same thing, right? Dropout and pooling will be done by PPU. Uh, and then obviously this encoding. So how the encoding works is that we will use two different data, right? So we have a data vector and index vector. So for a given let's say we have a weight matrix here, right? So we have a two number of channels is two, a number of weight matrices vector is two, right? So we have 3 by 3 of weight matrices. So we have number of zeros here, right? So that's partially. So how do we do that is that we just list all of those non-zero values. We just go from left to right and then top to bottom. So we just go from here to here and then just here to here and then just switch again and then just follow this route, right? And then we just list all of the non-zero values. And we have another vector called index vector. In the first index, we have the number of non-zero values. That's like 1, 2, 3, 4, 5, 6 or 6, right? And then we just we just write each of these, right? Relate all of those non-zero values to a given index. So how do you compute this? We just start from this, just start from the start, and then we have before 23 we have zero, only 1 0. So we just put a 1 here, and we just move then again. So we have 1 2 3 4 0, and then we have 18. So we just write 4 here, and then again we have 1 0, and this we get 42. So we just write 1 here, right? Because we're just counting the number of zeros in between the numbers, right? So after 42, we have 77. We don't have any zero here. So we just write 0 because we don't have any zeros here. Then we have 1 0, 2 0, 3 0, and then 24, right? So we have 3 zeros. So we just put a 3 here. And then 1 0, 2 0, 3 0, and then 8. So we have put 3 again. So that's like basically how the indexing works. So the index is actually 4 bits, right? So it can have a maximum of 15 in the values. So we can only have a maximum of 15 zeros in between two numbers. And if there are some other values, we have to put a 0 in the data vector itself. So there are special issues with this architecture. The first one is fully connected layers. As I have never mentioned fully connected layers here. So this layer architecture is not meant for fully connected layers. the authors assume that is a very small part, only 8% in AlexNet, 1% in GoogleNet, and 2% in VCCNet. So they have not optimized it for it, right? The issue with that is that the multiplier does the multiplication of all of the weights and all of the inputs, which will not be required, because for fully connected we only need to multiply a single input by a single weight, right? We don't multiply by all of the weights. So basically we multiply will only have 25% of throughput, or useful throughput. So that's an issue here. Another part is temporal tiling. So what it basically means is that some data cannot fit inside the IRM or ORM. That's like the input and output activation buffer inside the PE, right? So for that, we'll have to do temporal tiling. So basically, we have to store that into DRAM and just retrieve that again. So that's one of the uh, demerits for now. But obviously, that's only 9 of the 72 layers fit. So they didn't increase the number of buffer. For the configuration for the experimentation, they did the design configuration is listed here, right? So they use total number of 1024 multipliers, which will be split into 64 different processing elements. The IORAM and ORAM data would be a total of 1 MB, and the indices would be 0.2 MB. The accumulator banks is a 32 accumulator banks. So with and then the multiplier array is 4 by 4. As you can see here, we have 4 by 4 times. That's like 16 multipliers, right, in a single P, and we have 64 of those P, right? And then the accumulator will also will need to be 2 by times F by I, so that's basically 2 times 16 and then 32. So that's why we have 32 here. The weight we have will have 50 increase, and the obviously the IORAM, EORAM we have will be 10 kV multiply 16 bits, and the accumulator wide 16 bits. So that's like the specifications here. So they use synthesis high-level system C and catapult high-level synthesis to generate the Verilog, and then they design using TSMC 16nm FinFET for that. And okay, so the memory occupies a 57% area, and the multiply 6% area, as you can see here, right? The memory has the highest area. So these are the buffers and this weight, and then the IORAM. So these are the memories, which covers around 57% area and multiply around 6% area. So for the experimentation, they design a custom built cycle simulator and also use time loop, which kind of does all of the memory hierarchy, the data flow, and energy modeling, and the area part as well. So they use 3 different architectures. The first one is the DCNN, so that's basically the dense CNN, which both the dense activations and weights, and the dot product is been used for this. And then they again used a DCNN optimized. So for this, they used the same as DCNN, but the additional part is that just before sending the data to the RAM and before retrieving the data from the RAM, they kind of compress the activations value. And they also did some allocating for the multiplication. Another part is SCNN. As you can see here, all of these stats are same, but obviously the number of RAM is reduced because we'll be using compressed data, and that doesn't require a lot of different RAM. And obviously we have a higher area here because we'll be using accumulator buffers here, and the buffer banks will require more area, right? So that's why we have higher area for this. Okay, so and obviously wiring has been excluded. For the benchmarking, AlexNet, GoogleNet, and VCNet has been used. And then they have also do some synthesis for extensibility with sparsity. That's something that has been added. Uh, okay, so this figure is the same. So for the output, right? So first part is here in the y-axis we have the latency and the energy, and the x-axis we have weight by activation density. So that basically includes both the weight density and the activation density in the same place, right? So how it operates is that to the far right hand side, this is like when there is no sparsity or fully dense, right? And this is when there is highest sparsity. So we have to read it from right to left. So for the obviously for the low density, the SCNN works worse, right? Because it has some higher overhead of those accumulator banks, those cross bar circuits and stuff like that. But as sparsity increases, the latency reduces, and at some point, right, at 0.83, so that's like so 0.85, starts performing better, and at 0.83, it starts decreasing the energy, or having being more energy efficient compared to DCNN, and compared to DCNN optimized, it starts at 0.6, right? So at the densest, at the sparsest point, it has the around 6% of only energy consumption than DCNN, and 20% of DCNN optimized, right? So it kind of had a 24 times improvement in performance compared to DCNN, right? So sparsity matters even for the SCNN. And then looking at the different models, so for the comparison, they have used the DCNN, DCNN optimizer, the SCNN, as well as the SCNN Oracle. This is like the ideal case for SCNN when all of those modules are working parallelly. So as you can see here, uh, the obviously the speed up is quite high for SCNN, right? And the obviously the SCNN and ideal are working almost same, right? But as the layer increases, there is a huge gap in between them. Same is exists for each one of those, right? So the reason for this is that something called intra-PE and inter-PE errors, right? The first one is intra-PE fragmentation. So basically, what happens is that as the layer propagates, later layers will have lesser workloads for the PE, right? So that's why uh, the CNN cannot perform better. And then for the inter-PE is that as in the later part, uh, some PEs would complete their works faster, while some other would not do that at a time. So that basically the entire network has to wait for those PE to complete, and that's an issue there. So that's the inter-PE barrier, right? So this can be seen here as well. So this is the average multiplier utilization or the intra-PE case, and this is the average PE cycles or the inter-PE case. So as you can see here, the multiplier utilization reduces while the intra-PE barrier is almost similar, right? So because of this barrier, uh, the optimization cannot reach the ideal case, and because of the utilization reduction, the optimization is not increasing as much, right? So to compare this, the paper does changes the number of PEs to 64 and then the 4, and then compares the results. So they found that the 64P achieves 11% speed up. So what the paper concludes that addressing inter-PE is more critical than inter-PE. For the energy efficiency, it just compares the DCNN, DCNN optimization, and the SCNN. I mean, and obviously, the energy is reduced and in the later circuits, right? But in the first one, it is very high, right? It's because in the first case, it has the highest energy density or highest dense data because of the inputs will not be zero, right? So for that case, as you can see in the first, right? So when the density increases, the energy increases as well. So that's why we have the highest energy, but the overall we have 2.3 times less compared to the CNN and depends on the density as well. So so they also analyze the effect of weight sparsity and the activation sparsity. So they kind of did the same as CNN for only weights and they for only activations, and the entire have both. So what they found was that, as you can see here, like it's the same thing but only for activation and weights. So what they found was that SCNN or the using both would have 2.1 times and 1.6 times more efficient than SCNN activation and SCNN weights, and actually consumes more energy, less energy, right? So for the case of activation, right? So as you can see here, right? So for the sparse activation, at first it consumes less energy than both SCNN weights and SCNN as a whole, right? This is because it doesn't it doesn't use weights, and the weights in itself consumes 6.7 energy, right? So that's why it's doing better. But as sparsity increases, this number is actually reduced or actually diminished by the betterment of the weight sparsity in the data itself. So that's why at the end the SCNN performs way better than all of these other networks. So the key takeaways is obviously as sparse CNNs can heavily outperform dense CNN networks using both weights and activations, and its weight is better than using only one part of those. We have something called an inter-PE barrier, which needs to be focused more than the intra-PE fragmentation for improving the sparse architectures. And then using the compressed sparse activates improves the performance and also reduces the memory bandwidth. And then compressing this data can have help in a lot of different things, right? So it kind of increases the throughput and reduces the energy. And obviously load balancing and parallelism is required for interest for sparse architectures to maintain a very high throughput. Uh, that is all.